This is a quick video on random variables and how we can use them to solve problems. When I was a graduate student, Professor Liggett started his lecture on random variables with the following quote: "Random variable is actually a bit of a misnomer, for a random variable is neither random nor variable." There's so much truth to this. If someone were to tell me that a random variable is random, my first question, and it's a fair one, would be, what does that even mean? What is random? That requires a precise definition. Is there a true source of randomness in the universe? We suspect that there are, but if we're given a number, we cannot actually prove that it's random. Finally, the way that we use random in everyday language, we mean not predetermined. However, I'm going to give you an example of a random variable that is valid and entirely predetermined. So let's get to what random variables really are and how to use them. So a random variable is a function from a sample space to the reals. Now, there's often more subtlety in this definition, but for our purposes, it's good. Now, the important property is that for every point in the range of the random variable, the inverse image of it must be in the set of events. So I've drawn this here. So I have my random variable x, and here's its sample space, and here's its range, the reals. So I drew one point x star, and then I took the inverse of the random variable x, and I mapped it back to the sample space. So I have a little outcome, little omega here, and this whole set is E. Those are the events. And this event, E, can be empty. So when we say the event x is equal to x star, what we mean is all those outcomes in the sample space such that the random variable on that outcome equals x star. A fair question, and it's actually the fundamental question, is why do we care about defining events on random variables? And the reason we really care about that is because probabilities are defined on events, not on random variables. So if we want to use random variables to solve problems, we actually have to define the events in order to calculate the probabilities. And here is how we can think about that. So when we think about the event, the probability that x equals x star, and oftentimes we're a little sloppy in that we will just say the probability of x. We're not always so precise about specifying the specific event, but that's really what we mean. So in order to figure out the probability of this event, x equals x star, we examine the sample space for an outcome satisfying the condition. And then to find the probability of the event, we sum all the probabilities of the outcomes that we found in the first step. Okay, so now let's get to the examples. Okay, oh, I promised you a predetermined useless random variable, and here it comes. So I'm going to define this random variable x to be, on every point in the sample space, x is going to equal 1. And right here I've drawn an example of a sample space. This sample space is for tossing 4 coins. So this predetermined random variable I just specified, for every single set of tosses, it will just be 1. Entirely useless and entirely predetermined. So now, let's do something more useful. So let x, this random variable x, be the number of heads in 4 tosses. So we've drawn the sample space for the 4 tosses, and we're worried about the event of x equals 2. So now when I go back here, I'm going to say x star is equal to 2, and I've already highlighted in green all of the outcomes that are the inverse image of that. So map it out like this. Okay. So those are all those points in the sample space such that the random variable x equals 2. And if we're assuming that we have a fair coin, we have 16 total points in the sample space. So each outcome has probability 1/16, and we have 6 outcomes such that the number of heads is 2, so we have 3/8 probability of x equal to 2. So I hope this is helpful for you in thinking about solving problems with random variables.